The MOSFET behaves as a voltage-controlled current source. Let me explain that to you. It accepts a signal VGS between gate and source and provides a current GM-VGS at the drain terminal. And so it is a voltage-controlled current source, if you remember this topic from network analysis. Now the input resistance of this control source is very high, and ideally it is infinite. The output resistance, that is the resistance looking into the drain, is also high, and we have assumed it to be infinite thus far. Now if you want to draw a circuit incorporating all these features and wish to replace MOSFET by an equivalent model, we arrive at something like this. This is the small signal equivalent circuit of the MOSFET. And in our small signal analysis, we are going to be replacing the MOSFET by this model to aid our calculations. However, before we start our small signal analysis, some things have to be done. Firstly, find the DC quantities by shorting small signal input. Remember what we had studied in one of our previous courses, that the DC and the small signal can be separated. Secondly, you are to short DC voltage sources and open the DC current sources. After that, you replace the small signal equivalent circuit for the MOSFET and perform the analysis as required. So far, we have assumed the output resistance to be infinite. However, in reality, this is not the case. This was based on the assumption that the drain current in saturation is independent of the drain voltage. Now, we have seen that in previous lessons that this is not the case. The drain current does in fact depend on VDS in a linear manner. I am of course talking about channel length modulation. If you remember, the output resistance could be given by R0 equals the early voltage divided by the drain current. This drain current is of course the value without the channel length modulation, that is lambda equals 0. Now R0 has a very high resistance, but of course it is not infinite. It ranges from 10 kilo ohms to 1000 kilo ohms. In the circuit we can draw it, and it comes in parallel with the current source. Now if we incorporate this resistance into the voltage gain formula, we get minus Gm multiplied by Rd parallel with R0. This will obviously mean that the voltage gain will be reduced, but it will be more realistic. Now a little bit about the transconductance Gm. There are two more ways to express Gm. This one and this one. So we have a total of 3 formulas and all of them are equivalent. In your own time, you should look at how each of them are derived. The benefit of having different formulas for the same quantity is sometimes you are given one information and the other times you are given something else. So based on what you have, you can calculate the missing quantities. Now let's look at an example to see how small signal analysis is carried out on a common source MOSFET amplifier.